All right. So this paper is from November 2025, and that's going to be paper two. Um, and the first question is about the electric charge. The diagram shows the apparatus used to investigate electric charge. The equipment is viewed from above, and here what we are observing that ball one and ball two have positive charges. Ball one is fixed in place. Mm, okay, and ball two is attached to a rod that can rotate about P. So about P, we can say that means this is going to be your pivot, right? This is going to be your pivot. Ball two does not move. So, all right. So here's the force that is, acting in this direction, right? So this can rotate this rod anti-clockwise, right? Anti-clockwise by having this force acting downward, and it is 4.2 centimeter far from this point P, right? Now, state in terms of charged particles how balls have become positively charged. Yes, if anything has become positively charged body, so what actually has happened with that body? It must have lost the electron. Yeah. What do you people think? What happens
Yeah,
to that object? It must have lost the electrons, right? So, uh, the positively charged object is due to loss of electrons, right? So, how balls have become positively charged? The balls must have lost the electrons. Okay, right? Lost the electrons. Okay, so uh, yeah, that's all. The next part says ball one exerts a force F of 0.57 Newton on ball two. Ball one is here and it is exerting a force of 0.57 Newton on ball two. Okay. And are they both positively charged bodies? Yes. Yeah. This is the information that is given here. Both ball one and ball two are positively charged, right? So what we have learned that the same charges repel each other, right? So if somehow the ball one is going to apply force on ball two, so what will happen? The ball two will have to go downward, right? The ball two will have to go downward. So state the value of the force exerted on ball one from ball two. So is this something related to action and reaction? Yes. Equal and opposite reaction. What do you think? Yes. Equal and opposite reaction. Due to equal and opposite reaction, therefore, the ball two is going to exert the same amount of force on ball one. That's going to be 0.75 Newton. Okay. Calculate the moment on the rod from F1 about P. So, what is the perpendicular distance? What is the value of perpendicular distance? It is 4.2 centimeter. Okay. It is 4.2 centimeter, right? And what will be the amount of force? Yeah. What will be the amount of force? Yeah, this is going to be 0.57. The force is
yeah,
0.57 Newton, right? Okay. So therefore, if we want to calculate moment, So 0.57 times 4.2. So what answer are we getting? Please do this quickly. What are we getting? Yeah, what are we getting?
2.394.
2.39. That that can be 2.4, right? And you can see Newton centimeter unit is there. Therefore, I have not changed this unit. Okay, this unit there, because they have mentioned Newton centimeter because they want the answer in Newton centimeter. All right, now state the magnitude of movement about point P due to the force from the spring. If you refer the spring, yeah, force from the spring, uh, so force from the spring, it is in this direction, right? And it's going to be this much, right? So what they're asking, state the magnitude of the movement about P due to the force from the spring. Yeah. So mm, about P due to the force from the spring is to make magnitude of moment. Is it going to be to balance? Are they saying to balance?
Can you go to the diagram?
Yeah, I'm on the diagram.
It shouldn't it be the same since the anti-clockwise moment
Yeah,
equals clockwise?
yeah, but they need to mention this thing in the question to balance it, okay? Right? What amount of magnitude of movement? State the magnitude of movement about point P due to the force from the spring to balance, okay? To keep the system or the rod balanced. Then it will be easy to, identify that they are asking about the equilibrium condition, right? The sum of the clockwise movement equals to sum of anti-clockwise movement. Okay, so movement is going to be same, that is 2.4. Okay, 2 to keep the rod balanced. Now draw an arrow on the diagram to show the direction of the force that the rod exerts on the spring. Yes, draw an arrow on the diagram to show the direction of the force that the rod exerts on the spring. Yes. Hmm. So force is exerting in this direction, right? Yeah, to keep it balanced. Clear? Right? This question is about gravitational field strength. The table shows gravitational field strength at the surfaces of four different planets, diameter in kilometer, and gravitational field strength in Newton per kg. Give a reason why a scatter graph is the correct way to display this data rather than a bar chart. Okay, so we have diameters in kilometers. Uh, okay, the planet have the same mass but different diameters, right? Give a reason why scatter graph is correct way to display. Whenever we have scatter, scatter graph, a graph which, which gives the continuous reading. Okay. So we do not plot the bar chart. Okay. So bar chart is actually the data which is based on the digital form or digital data, right? Or discrete form, discrete data. But when we have the scatter graph, the scatter graph has the continuous data plot. Okay. A student claims that the relationship between gravitational field strength and the diameter of a planet is given by this formula. All right. Gravitational field strength times diameter square equals to constant. Using data from the table, evaluate student's claim. Is this clear? What we have to do? Gravitational field times diameter square. Are we getting a constant number? Are we getting a constant number? Can you please do the calculation? 13,000 square times 9.8, 18,000 square times 5.1. Are we getting a constant number every time? Yes. We have to show the
Yeah.
calculation, right? Of each
Yeah.
row, at least 2 or 3 rows. So 13,000 square times what it 13,000 square times 9.8. What are we getting here? And then we have 18,000 times 5.1. 18,000 times 5.1. Are we getting same answer, please? Could you tell me the value? 13,000 square. That's going to be 169 and two zeros, two zeros, and two zeros, right? Times 9.8. What are we getting? All right, let me do it.
1.65 times 10 to the power of 9.
1.6 10 to the power 29,
9.
right?
No, not 9, 9.
Oh, right. And what about this one? Are we getting the same value?
Yeah.
All right. So it's going to be around by 1.6 into 10 to the power 1, 2, 6. Okay. So we are getting the same constant value, almost approximately we are getting the same answer. So by doing this calculation, we will get 2 mark. Okay. And then upon conclusion, okay, with a comparison of at least 3 or 4 values, we can get 4 mark. Okay. So the student's claim is correct as uh, 2 rows are giving the constant same value. Okay. The diameter of a planet affects the gravitational field strength at the surface of the planet. Diameter of a planet affects the gravitational field strength at the surface of the planet. Okay, which of these is also a factor that affects gravitational field strength? Yes, gravitational field strength can only be affected by mass or by color. It should be mass, right? Okay. Heavier the mass, greater the gravitational field strength will be. Okay. Now here we go with question number 3. The diagram shows some of the parts of hydroelectric power station. All right, there's a powerhouse, there's a turbine, the water discharge is there, water flow, there's a dam, and the turbine, works, generates the electricity, and then through the transformer, it goes on to the high tension wire. Water enters the turbine with a momentum of 120,000 kilogram meter per second. State the formula linking momentum, mass, and velocity. So that's going to be momentum equals to mass time velocity. A mass of 14,000 kilogram of water enters the turbine. Calculate velocity of the water as it enters the turbine. Calculate the velocity of the water as it enters the turbine. Okay. So we know the momentum. We know the mass of water. We can easily, first of all, we have to make a data. And the mass is 14,000 kilogram. And we can make V subject, V equals to momentum over mass, right? So we just plug 120,000 and divided by 14,000. So what are we getting here?
8.6.
8.6, okay. 8.6 meter per second, right? The 14,000 kilogram of water leaves the turbine. This water has a momentum of 63,000 kilogram meter per second after it leaves the turbine, right? This water has a momentum of 63,000 kilogram meter per second after it leaves the turbine. Okay, this is going to be the final momentum, right? Okay, all right. So the turbine exerts a force of 6,100 Newton on the water. Calculate the time taken for the water to pass through the turbine. So if you recall the the definition of force with in terms of momentum, it is rate of change of momentum divided rate of change of momentum is called force, right? So we can have the change of momentum, right? And we have the force that is exerted on the water, and then we can, make a subject T, right? Okay. So what is the change in momentum? This is first of all we have to do. Okay. Change in momentum has to be calculated first, right? So initially it was how much? It was 120,000, right? It was 120,000 initially. So initial momentum was because delta P means the change in momentum, right? Okay, that is change in momentum. And for change in momentum, we have to have the initial and final values. Okay, so initially we have 120,000 kilogram meter per second, and final momentum it is 63,000 kilogram meter per second, right? Uh, and then the force that is exerted is 6,100 Newton, right? And we have to find out time. Okay. So in order to find out change, I can subtract this 120,000 and 63,000. So we'll get how much value? Please tell me the value. What are we getting? Yes. What are we getting here? It's
57,000.
57, 57, right? 57 kg meter per second. Okay. And the force is there. We can easily, divide this uh, the change by force, right? So it's going to be 57,000 by force, which is 6,100, right? So what are we getting here? It's going to be 7.
Nine
It's going to be
point three.
9.3, right? So it's going to be 9.3 seconds. Clear? Right? Now, as the water passes through the turbine, energy is lost from the water's kinetic energy store. Explain what happens to the energy lost from the water's kinetic store. Okay, it must be transferred, right? It must be transferred to other form, and it is lost in the form of heat as well. And some work is done, right? Yeah. Yes, as the water passes through the turbine, energy is lost from water kinetic energy store. Water's kinetic energy. Okay. So explain what happens to the energy lost from the water's kinetic energy. Okay. So uh, kinetic energy of water is transferred when the work is done. Work is done to um to move a turbine, right? To move a turbine. So kinetic energy of turbine increases or not? Kinetic energy of turbine increases, right? Yeah. Hello. Is this clear? Are you getting this?
Yeah.
Okay. Kinetic energy of turbine increases, and then what will happen? Some of the energy. Okay. Some of kinetic energy store of water. Some of the kinetic energy store. Some of kinetic energy store of water uh, is lost uh, in the environment. Jazakallah, thank you very much. In the environment, or we can also write surrounding, okay, in the form of heat, right? The form of heat, right? Is this clear? Hello, everything is clear? All right. Now, hydroelectric power is an example of renewable source resource for the generation of electricity. Give two examples of non-renewable resources for the generation of electricity. Yes, non-renewable. Yeah, two examples of
Uh,
non-renewable.
non-renewable
Yeah.
coal and oil, yeah, fossil fuels and
Okay. Yes,
uranium,
yes. Fossil
nuclear.
fuels. All right. Yes. Okay. So coal, gas, right? Nuclear, or fossil fuels. Okay. This question is about sound waves. Type sound waves. Are sound waves coming?
No. No.
Okay. Oh, okay, okay. Did you find this question last to last year in your paper I gave in the assessment? Okay. I took it from here. I think so. I think so. That was a similar question. All right. So magnetic field is not included in the syllabus right now. Wavelength. Okay. So space is there. Space physics. Space physics. Okay. Now, a student investigates how the temperature of a metal block varies with time as it is heated. The student measures the temperature of the block at 5 minutes intervals for a total of 30 minutes, right? So mm, the the rise of temperature is there, right? Till 15 minutes, right? And then temperature becomes constant at 450 degrees Celsius, right? So give the name of a piece of equipment that the student could use to measure time during the investigation. I think it's a very simple question, right? Yes. Give the name of piece of equipment that the student could use. What do you think? What could be the answer?
Stopwatch.
Yeah, it's stopwatch. Okay. Stopwatch, or even you can use a timer. We can say a clock. Okay. Which of these is the dependent variable in this investigation? Dependent. Yeah. So which variable is dependent? Mass of the block, temperature of the mass of the block cannot be dependent. Temperature of the block, time or volume. Oh, so simple. It's again very simple. Yes, it should be a temperature, right? Temperature of the block is the dependent variable, okay, in the investigation, right? The energy supplied to the block is 440,000 joule. Calculate the mass of the metal block when the temperature of the block increases from 45 degrees Celsius to its melting point of 450 degrees Celsius. It's okay. Listen, listen. The energy supply to okay, so increases from 45 degrees Celsius to its melting point of 450. Okay, so what we have to do? Calculate mass. Okay, calculate the mass. Right. Yes. So specific heat capacity. If you guys remember, what formula that we use for the specific heat capacity? Yeah.
Delta Q equals MC delta T.
I'm I'm taking class. Yeah. Sorry. Yeah. So what's the formula that we use for this?
Delta Q equals MC delta T.
Delta Q equals to MC delta T, right? So where this delta Q is the change in heat, right? Or energy transfer, right? It is also equals to energy transferred. And this is mass, okay? And this is this specific heat capacity. And this is change in temperature, right? And make sure that there should be no change in state, okay? All right. So first of all, uh, uh, we have to find out the change in temperature. So we are starting from 45 degree, right? When the temperature of the block increases from 45 degree to its melting point of 450 degree. So there is a change in temperature, which is about 450 and 45. So it's going to be 405 degrees Celsius, right? There's a change in temperature, which is 405 degrees. Okay. Now, what we can do is, since we already know the how much heat is supplied, right? So it was 440,000 joule, right? So we can make M subject delta Q over C delta T, where delta heat which is going to be 40,000 divided by the specific heat, which is 910 joules per kilogram per degree Celsius times 405. So what are we getting here? Yeah. Yes. What are we getting? 440,000 divided by 910 times 405. 0, 0 divided by 910 and then divided by 405.
1.1, 1.2.
Okay, 1.19, which is going to be 1.2, 1.2. Okay, right? 1.2 kilogram, the unit is already mentioned. The metal block melts and then the liquid metal boils to become a gas. Describe the motion of the particles when the metal is a gas. When the metal is a gas. Oh, they are just asking what is the motion of the gas? Yeah, how the particles move in the state of gas. They move, their motion is random, right? Yeah, the motion of gas particles is random. Okay, and what do you think? What is the speed as compared to solid and liquid? The speed is high as compared to solid metal or liquid. Okay, right? Now suggest two changes to the graph if the student had used a different metal in their investigation. Had used a different metal in the investigation. Okay. Yes, two changes to the graph. Yeah. What could be the changes that we can have when the metal is changed or metal is different? Definitely the rise of temperature would be different. Yeah. The rise of temperature would be different and the melting point that it reaches to this level would also be different. Okay. Yeah. Right.
Yeah.
So the rise of temperature would be different. Uh, the rise of temperature would be different. I can also say the gradient would be different. Okay. And the third is what we can say, the melting point. Yeah. The melting point would also be different, right? Okay. This question is about okay, yeah, it's radioactivity, so it's not included right now. Oh, that's all. It's P2 is done. Whatever the things that are coming in P2 is done, right? Sorry, not P2, in the assessment. Okay. So I'll share this paper, inshallah, with you. Okay. By email. Allah Hafiz. Assalamu alaikum.
Wa alaikum salam.